Hi there, welcome back to the breadboard. What you're seeing on the screen here are a view of a REYAX RYLR896 transceiver. REYAX has kindly sent me a pair of these to play with, and to make a video I was interested in doing some longer range I/O remote sensing devices, and these appear to be ideal for that kind of purpose. So I got them just a little while ago. I've been playing around getting some code up and running because I couldn't find very much available for Arduino IDE or any other language really to talk to these in a efficient and basically trouble-free manner. So I wrote my own. This is what the module looks like. This is the front and back view of them. They're about the size of a stick of gum in total, including the antenna, but about a half a stick, so it's about 1 inch by 2 inches in sort of size here. They've got these pins along the bottom which make it great for plugging into a breadboard, as you'll see, and the pin out is designated on the bottom. They're very, very simple to interface to. They're 3.3 volt operation nominally. You've got your VDD for plus 3 volts and your ground for 0. You've got a transmit pin and a receive pin. These are 3.3 volt compliant, and you have a reset negative low. So you take that pin low, let it go back up again, and you can reset the radio on the board. Also on the back, but not populated, you'll see that there's a position for 2 LEDs and associated resistors. If these were in, it would increase the power consumption of the board, and these are designed for low power applications and things like that, so you really wouldn't want to do that. On the front of the board, you can see here we've got the RYLR890 transceiver module. This is actually based on a Semtech wireless and sensing transceiver. The data sheet I'm showing you right here, I'll include a link to it in the description so you can have a good look through. The chip itself is not exposed outside of the board, so I'm not going to go into details about it very much, except where it pertains to using the module for our experiments. So that's basically inside this can here. Down here we have another, and the controller here is an STM32F151. Quite a capable device, running as a front end for this. And what it does is it basically simplifies the interfacing to the transceiver so that you're reduced down to basically an AT command set. What's an AT command set, I hear you say? Well, that's something that goes way, way back to original modems back in the 80s and 90s, where getting online meant using an analog phone line and a modem with acoustic couplers and things like that. And the way you talk to those modems, you could send commands to them, was through AT. So it would be literally the characters AT plus, and then you would set things like the baud rate and things like that. I think it might have been a little bit past the ones with the acoustic couplers, but it was that kind of era, 1980s, early 90s, before the internet really took off. Anyway, it stuck around for a long time because it's very easy for people to understand and to present a simple interface for IoT devices and basic communications. And in this case, they're coupled with the Semtech transceiver and providing us the ability for very long range communications in IoT world. And these things are designed for IoT based applications. Just bring up here we go. So the boards, they operate at 915 megahertz, or they can work at 868 megahertz. Let's just bring down the specifications for this. You can also get versions that are working in the 400 odd megahertz as well. But for North America, you're actually only supposed to be using 915. So a few of the features that are in here: controlled easily by AT commands, 127 dB dynamic range, high sensitivity, low receive current. We'll have a look at that in a moment. You can get them with PCB integrated antennas. The ones I have here have little curly bits of wire on them, which is going to be a more efficient transmission and reception. It also implements AES-128 data encryption if you want, and we'll look at that when we're going through the command sets on how you would set that. Operating temperature -40°C to +85, so pretty much anywhere in North America would be fine to use this, even in outdoors, unconditioned environments. Dimensions 42.5 millimeters by 18 and a bit millimeters, so a little bit less than an inch by not quite 2 inches, by 5.5 millimeters deep, and it weighs only 7 grams. So power supply, as I mentioned, 3.3 volt nominal, anywhere between 2 volts and 3.6, but I would suggest you just treat it as a 3.3 volt device. RF output power from -4 dBs up to 15. It actually defaults to 15 dB output power. Insertion loss sensitivity -148 dBm. RF input level 10 dBm. Frequency range, so here we go, 862 up to 1020, but nominally 868 or 915 megahertz. And the AT command set kind of restricts you down to just these two, even though the chip inside is capable of a lot wider. Frequency accuracy, ±2 parts per million. Communications range, okay, this is where it really gets interesting. So it's claiming here for 4.5 up to 15 kilometers, and the 4.5 is typical range with a maximum of 15. Of course, that'll depend on your terrain, weather conditions, and what parameters you set up in the radio transceiver as well. Transmitting current is 43 milliamps. That's not a lot, but it can, rapidly diminish a small battery if you're sending frequently. But we'll get into the whole bit about how often you can send data a little bit later in the video. When you're in receive mode, it's down to 16.5 milliamps, which is quite reasonable. And then you can go into sleep mode, where you're only consuming half a microamp, which is really, really low power. So most of the time, these modules are going to be sitting in their receive mode. I would suggest that if you're implementing some kind of application where you don't need to transmit or receive very often, you could probably put this thing to sleep for maybe 5 minutes at a time or 10 minutes at a time, wake it up for a few moments or a few minutes, transmit a little bit of data, then go back to sleep again. Baud rates anywhere between 300 and 115 K2 with the bits per second. Now, obviously at 300 baud, that would handle a very slow processor quite easily, but it would take you a while to send a message into the module to be able to transmit it. Digital high and low voltage levels, again, typical thresholds for 3.3 volt logic. 300,000 cycles for the internal EEPROM. So that's your basic specifications. Now, for these modules, let's go have a quick look now at the command set for these. So let's just flip to here. Let me get a little bit bigger. There we go. So this is the same for a lot of these different modules. The 405 and 406 are the ones that are running at the 400 odd megahertz ranges. The 895 and the 896, I think, are the ones that run at the 800 megahertz, just basically sub-gigahertz ranges. Some of the things that you can use, as I said, all the commands start with the AT plus text being sent into the serial port. So you can set the address of the module. The address is regarded as the identification of the transmitter or the receiver. Do not confuse this with network ID. Network ID allows you to group a whole bunch of transceivers into a single network, and if you're not on that network ID, you don't receive the data irrespective of the address, and the internal code of the module takes care of all that for you. The address by default is set to 0, but you should really change that in your application to something different. Same goes for the network ID. The network ID, as I just said, was recommended range between 1 and 15. The address can be up to 65,000. Network ID 1 to 15 allows you to isolate groups of sensors, or groups of IoT transceivers. The band is where you would set the 800 odd megahertz or 915 megahertz. The parameters allow you to control things like the spreading factor, the bandwidth, the coding rate, preamble, that's number of bytes of preamble, etc. Now, a lot of these parameters can significantly impact the speed at which you can send data. But the faster you want to send it, the less reliable it will become. So by having, for instance, more preamble, that allows, when you're transmitting, for the receiver to get a better lock on your signal before you start sending the data. If you keep that a lot shorter, you better have a very strong signal or be quite close to the transmitter, otherwise you stand a chance of not getting a clean reception of the data. Same thing goes for the bandwidth, right? Wider bandwidth means you've got a better chance of keeping a lock on the signal and things like that. So these all have an impact on how fast the data can be sent. And in the examples I'm going to be using here, I'm leaving these at their default parameters for the moment. And I'll do in a later video, we'll start playing with the parameters and see how much of an impact it has. There's an online calculator for Airtime, how long it takes to send a typical message. So we'll get to that in a moment. Let's just go down this command set and have a look. So if you just send simply AT on its own to the module, it should send back to you an OK, and that's all it will do. If you send a reset, it'll respond with AT. If you send AT plus reset, it will respond to you with just plus reset. There is no polling the module for any data responses, even received messages over the air. It just literally, when it gets it, it just sends it out of the serial port, and it's up to your serial interface on your microcontroller to capture that and put it somewhere or deal with it. It won't store it internally and wait for you to interrogate it to see if it's got any data. So be warned of that. It caught me for a minute before I figured out the best way of handling the reception of this. And the same thing goes for these OK responses. When you send any command, if it's successful, it'll send you a plus OK back out the serial port. With the exception of the reset. So when you set the mode, which is you're either in sleep mode or you're in transmit and receive mode, it returns with OK, and you just say AT mode equals, and then it will be either a 0 or a 1. If you send a AT mode plus mode question mark, that says, and the question mark bit is for a lot of these parameters, tell me what you're currently set to. And so in this case, if we were in sleep mode, it would return AT mode equals 1. Set the UART baud rate. The default is 115K2. I just leave it at that rate because my microcontroller can easily handle it. But you can see you can set any standard baud rate from 300 all the way up to 115K2. And you literally put in the baud rate here. So you could, if you really wanted to be awkward, set it to some really weird value. I would imagine that would probably still work. And what you send here, here's an example of what you would send. AT plus IPR equals 9600. And it would respond with OK if it accepted that. If you do the question mark, it'll obviously tell you what it's currently set to. But of course, theoretically, you already know what it's currently set to because it wouldn't have received the IPR question mark correctly if you weren't already talking at the correct baud rate. Little quirky thing there. Okay, AT plus parameters. This is the one that affects more significantly the transmission speed. So we've got the spreading factor, the bandwidth, coding rate, and programmed preamble. The spreading factor between 7 and 12. Anyway, the range is from 7 to 12, and it does affect the bandwidth. Usually if you got a shorter, it does affect the transmit time. Usually if you're working on a smaller range, you can get away with a lower value. For bigger distances, you increase it to 12. Bandwidth, you've got 10 options here, ranging from 7.8 kilohertz all the way up to 500 kilohertz. The higher the bandwidth, the faster it can transmit the data. So if you're at a lower bandwidth down here, and some of these are not recommended, they're outside of the LoRa specifications. Oh, yeah, that reminds me. These are designed for LoRa, but these are primarily intended for things like LoRa interfaces and things. So LoRa basically means long range. That's really all it stands for. Anyway, these will be outside of the LoRa specifications, but all of these ones are viable. The narrower the bandwidth, the longer it'll take to send something. Again, we'll look at the calculator in a minute and you'll see the effects it has. The default is 125 kilohertz, and that's what I'll be using. The coding rate 1 to 4, default being 1, and the program preamble is 4 to 16, with the default being 4. And this is the number of bytes of preamble before the module would start sending data over the air. Now, some of the things that you don't get to see from this interface is things like how big the real packet is. You send your data and a few other things, but there's going to be the preamble, its address, its network ID, and a few other things being sent over the air, so that the receiving radios, because they're all going to receive the signal, are able to quickly dismiss and drop any radio receptions that are not meant for this module or this network. So, and here's an example. You put them all comma separated. So this is 7345, which would be a spreading factor of 7. So that's on the lower end. The bandwidth of 3, which would be spreading factor 7. Yeah, bandwidth of 3, coding rate of 4, and preamble of 5. That would be what that example would do. If you do the question mark at the end of AT plus parameter, you'll get back what it's currently set for. Setting the band, for mine, it's 915 and loads of zeros. Depending on your region, you might want to set it to 8685, which is, I think Europe uses that frequency range. The address of the module you can set anyway. Yeah, I was correct, 65,535. So that's a lot of LoRa modules you can have on one network. Defaults to 0 just so you can get things going, but you really should avoid using the 0. So it's simple enough. AT plus address equals 120 would set it to 120, and that is stored in the EEPROM so that you don't have to keep writing it. Network ID, anywhere between 0 and 16. Again, default is 0. The 0 is the public ID of LoRa. So if you want to have something more private, then you would use a different network ID than 0. You would set it, in this case, example would be 6. Again, when you set this, it just gets a plus OK response. What else do we have? Okay, this is where we were talking about AES 128 encryption. So here you say AT plus CPIN, and it's a 32 character long hexadecimal password. So you can see there you could create quite a complex long password for this, and only modules that have the same password in them will be able to decrypt the data and give it to you. I don't know whether it would still receive the data and just present you garbage. We'll have to experiment with that perhaps later in the video if it doesn't run on too long, but it certainly inhibits you from being snooped on by somebody. And I mean, that's a lot of variations to sit there going through programming in order to try and bypass that. Yes, a brute force attack on that, if somebody had the module, could finally hit one that does receive things properly, but is it really worth it? Probably not. RF output power, AT plus CRFOP, set the range from 0 dBms up to 15 dBms, and the default being 15, which is the maximum power. If you're running this in a local kind of arena, just a few kilometers between everything, you could probably bring that right down and be nice to your neighbors. The main command that you'll use in most operations is the AT plus send, you have to send a few things in there. So the network is handled outside of your normal control. So once you set the network ID, it stays there. When you're doing the AT send, you send the address. So anything that is listening on that address would get the payload length and the data as part of the reception. And so what you've got is the address, as we said before, anywhere between 0 and 65535. When 0 is the public one, remember, and within the network. So if you're just broadly listening, you'd probably go to 0. Payload length can be anything from basically 0, although there never really will be 0 if you think about it, up to 240 bytes. Now the transceiver has 512 bytes inside, but it by default it splits it in two, so that you got 250 odd bytes for receive and 250 odd bytes for transmit. And it tries to keep them separate. The reason why this is 240 bytes is because you do have to have bytes for the command and network ID, etc. to be included. This number of bytes is only the payload bit. So in here the example is hello, which is 5 characters, and the number of bytes in the payload is 5. But this 240, you can't use 255 because you've still got to have AT plus send equals 50, 5 as part of it, and then you're going to have the network ID as well, and perhaps the preamble, etc., etc. So this is reserving a few bytes for that information. Now, there's a little bit misleading here. So when you send, you will get a OK back. Now, when I first started talking to this module, I was a bit confused that there wasn't some kind of status, and all the data I could find initially didn't tell me whether this OK response came back as soon as the AT plus send, etc., hello was received by the transceiver, or whether it didn't send it back to you until it had literally sent over the air the message. Now it appears from my testing that it actually does wait until it's sent it over the air, because in my default this would take about a second to send over the air, and I don't get the plus OK back until around about a second after I've given it the command to send the data. So that's useful to know that if you get the plus OK back, that means it's probably successfully sent it. Doesn't mean that anything received it. It means it successfully sent it only. All right. Now the receive bit here confused me a little bit to start with, because it shows here, following the same examples of all of these, it doesn't have the AT plus, it just has the plus send. And what it's actually, so you don't do plus receive to pull the data out of the module. You don't do AT plus receive either. If you try any of those, you will get an error message. But if all you do is listen to the receive port without sending anything, you will get messages arrive, and what will come out of the serial port is plus RCV equals, and then it's got the address, and then so who sent it, I think who sent it. Actually, I haven't tried that. I'll have to recode my example. I'm using the same address on both ends right now. So the address, the length of data that's here, and then hello. These last two ones are the signal strength indicator, so RSSI, very common to a lot of radio communications figure, and the signal to noise ratio, which is in dB as well, I think. So a little bit of extra stats that you could use to show how well the signal strength is from the receiving station, from the transmitting station. AT-ver with a question mark, that's all you can do here. You can't set the version. It gives you the version of the software and the hardware, I guess, the firmware anyway, and it should respond something like RYLR896C_V1.0. Now obviously as time goes on that may increase in the version numbers. AT factory sets a factory default, basically resets the entire board. If you've got all of your settings all messed up, you can reset it. Here are all the defaults. So the band would be 915, 115 K2 baud rate, spreading factor 12, bandwidth 125, etc., etc. Other messages after reset, you may get a plus ready. I haven't actually been able to capture that yet with my Arduino, but apparently it does send it. And the next bit, which is important to know about, are error codes. So you don't send anything to interrogate the error codes, but these are the errors you may get back when you're sending commands, or if a reception takes too long. So a message coming in, I guess. The first one is you always, whenever you send your messages, so if you go back up and look at one a second. Not that one, let's pick this one. So AT send, payload length, and then the data. What you have to have on the end of that is a carriage return line feed, so that the module knows that it's got the whole data. So you can't have carriage return line feed as part of the data unless you escape it out somehow. But as soon as it sees the carriage return line feed, it says that's the end of it, now go process it. It might be a command, it might be a message to send. Well, that's still a command, but anyway. So you have to have ODOA at the end. What I'm doing in my example is having a /r/n rather than use the serial.println command. That way I have tighter control of what I'm doing. If you forget to put the AT command in the front of a command that you're sending, you'll get an error too. If you don't have an equals and you're not doing a question mark, because as you remember, some of these have question mark, right? AT plus the question mark, not an equals. But if you're sending a command rather than a query and you don't have the equals, you'll get an error 3. If you send it a command that it just doesn't know about, well, error 4. So in transmitting, if you get an error 10, that means that it took too long and basically, I think, gave up trying to transmit the message. I'm not sure why it would do that, but I guess if internally something went wrong, that's theoretically what it would send back to you. Receiving is an error, a receive error. So took too long to receive a message. Error 11. CRC error. I'm guessing this is sending CRCs to and fro as part of the communications. It will send you an error 12. If you try and send too big a payload, so in other words, you've told the maximum payload it'll accept is 240 bytes, but if there's, say, 250 bytes before the carriage return line feed, it should send you an error 13 back, and then if it doesn't know what the error is, it'll give you an error 15. Sorry, that previous one was an error 13. And if it doesn't know the error, it'll send you an error 15. Yeah, so that's really the catch-all. If it doesn't know what's really going on, if it's none of these, it'll give you the 15. And that's pretty much all the information that I could find. When I went Googling for example code and things like that, all that anybody was doing was they weren't really playing with the parameters. They were just doing an AT send and then giving it a message to send, and then doing, okay, now just sit there doing some receives and don't do any sends. So they had one set up as a transmitter and one set up as a receiver. It all worked very, very well, but it wasn't really very useful. So we're going to look at the code in a moment, but let's first of all have a look at the Airtime calculator so that you can see. Now this is for LoRa modem settings, and some of these things are, there are some protocols. One of the reasons this is a free-to-use module, you don't have to get a license for it or anything else, but there are constraints on what you're supposed to adhere to when you are using it. And one of them, I think, is that you need to only use 1% of the airtime per module. So if, say, you've got 100 seconds, you're only allowed to use 1 second of transmitting every 100 seconds. If your transmission takes 5 seconds, then you have to wait 500 seconds before you can send another message. And depending on your configuration, it could be a lot worse than that. So I think what I was using was a spreading factor of 12. My payload length was 13 in my example that we're going to show you. But if I set that to 240, which is the maximum, the preamble defaults to 8, I think, or more. Then this calculates how long it'll actually take sending a message that is LoRa compatible. And the whole point about LoRa is it's long range, hence the name, and it needs these extra preamble and time to send the message so that it can be sent reliably. So when we look at it, our preamble length is 400 milliseconds. That's getting close to half a second just to send the preamble before we even send the data. Right? Symbol length, so each piece of the data is 32 milliseconds long. Symbols in the frame, 248, so our message is 240. We've got 8 more here, so the preamble as well. And then the time on the air to send this message is 8.5 seconds, which means that we can only send one message every 14 minutes, 13 seconds. This is sticking to the LoRa specifications, and I suggest that if you're going to participate in this, that you really should be, behave well. I mean, obviously, if there's an emergency situation that your modules come up with and it needs to get some data out quickly, then maybe you could break that the odd occasion, but really you should try and play fair with everybody else and stick to these recommendations. Now, I don't know, I haven't found any specific code yet that can let your application calculate this so that you can actually automatically adjust your duty cycle of sending based on what you're sending. What I've done is I've just basically put in my parameters, which I think my my payload length was 13 characters approximately. My preamble was set to 4, so you can see here now my airtime is just over 1 second, which means that I can't send anything more frequently than 1.42 seconds, so about 100 seconds. Now, if I change my bandwidth, for example, to say 500 kilohertz, so this was 125. If I go up to 500 kilohertz bandwidth, you can see now it takes only a quarter of a second to send that same amount of data that took just over a second before. So I went from 125 up to 500, so that's 5 times the bandwidth, and it's taken a quarter of the time. But it now means I can also send a message every 26 milliseconds. But that's taking up more bandwidth, which means that you probably have less radios on the air, or they'd be talking over each other. So if I put it back to 125, another thing that you can do is shorten your preamble, but I think 4 is the least you can have. You can set 1, but that really, the preamble, as you can see there, doesn't make a lot of difference. So I had 4, right? It's only adding, if I make it 10, right? It's not adding, it's only adding a couple of 100 milliseconds. So my 8 is perfectly fine, I think. Payload length obviously has a significant impact on it, but your spreading factor, I think, is what also makes a big impact. So if I go down to 7, this is, I think, spread spectrum, I think. We'll have to look at the specs in another video to try and figure out some more of this. You can see now the time on the air is only 56 milliseconds, which means we can send a message every 6 seconds. All right, but this is going to probably be less reliable with a spreading factor of that. With it at 12, it takes longer to transmit, but it's going to be more reliable. So as you can see, a lot of these parameters will impact how quickly you can send your messages over the air. So yeah, the spreading factor is one of the biggest ones that impacts the speed, that and your data length. And of course, having more, taking up more bandwidth. So if there's not many modules in your area, you could probably increase your bandwidth and get things going faster as well. In my case, and in my example I'm using, I can't send a message any quicker than about 1 second. So that's the calculator. I will provide a link to the calculator so you can use it yourself for the module. And Reyax doesn't seem to have any forums or anything like that here either. Not that I could find, but that's okay because I wrote my own code based on the specifications. So what am I using now? Let's get on a bit more. What am I using for driving this? I am technically using 2 of these. This is an Arduino Nano 33 for IoT. It's already got a Wi-Fi Bluetooth built into it, but I'm not using that in this example. I'm just using it as an Arduino. And it's running a SAM-D21 microcontroller on here, so it's actually quite a fast microcontroller. But this code will happily work on pretty much any Arduino, even an Arduino Uno, etc., etc. Just bear in mind it is 3.3 volt logic on here, which is why I picked these, because these Arduino Nanos are 3.3 volt, the 33 IoTs. They are already 3.3 volt ones. If you're using an Arduino Uno, it's 5 volts, so you may have to have some level shifters to talk to it reliably. It doesn't take much actual effort to do that. A simple resistor divider would be more than enough. The data coming back out again from the transceiver module would easily go into the Arduino and be recognized, because the logic levels still cover the thresholds that 5 volt logic requires, even though it's 3.3 volts. So that's perfectly fine. So this is what I'm using. I've got the transmit and receive. We actually have two transmit and receive. So you've got a serial and a serial 1 on the AT Nano 33. You've got the one that comes out the USB port, which is the one I'm using for sending out my debug messages. And then we've got the serial 1, which I'm using to talk to the Reyax transceiver. I'm also using, in this case, PB11 and 10 for, well, sorry, D2 and D3 using Arduino pin speak. PB11 and 10 are the internal peripheral bank B pin 0 and 1. Anyway, I'm using D2 and D3 for the driving the LED and the reset pin of the transceiver. I've got a little external LED connected. And what I've also done is I've hooked up a DHT22 temperature and humidity sensor onto D21 over here, so that I can receive a temperature and give me something a little bit more exciting to send over the air. I'm not going to go into how you use a DHT11 in this video. This is all about reviewing the Reyax transceivers. I'm just giving you an idea of what I've got set up. Now, the other part of my setup, I have a second Reyax transceiver right here connected to my Automation Direct P1AM-100 Pro Open Arduino compatible PLC. Now, as it happens, it has the exact same SAM-D21 microcontroller inside this as the one I'm using on my board down here, just off screen slightly. And so what I've done is I've got the GPIO module that Automation Direct kindly sent me, and I've just hooked up the transceiver directly to the GPIO module. And what these pins are here, they're connected effectively directly through to the SAM-D21 in very much the same way as the Arduino IoT33 module is connected to the transceiver as well. The only difference is there's a little bit of protection circuitry inside this GPIO module, just in case you accidentally touch one of the pins for a very brief moment with, say, 24 volts. If I did that on the if I did that on the Arduino Nano 33, I would fry it pretty much instantly. But that's really the only difference in the example we're doing here. And I'm only using this because I happen to have it here. It is already 3.3 volt logic, so I don't have to use any level shifters. And I can just hook it up and use it as a remote end to my little scenario to show you these things working. So what's my other end? Let's just flip to that. There we go. So this is what I have on the breadboard. I've got my Arduino Nano 33 IoT. I've got the Reyax module here. You can see how small it is. I just plugged into the breadboard. I've got transmit and receive connected across to the transmit and receive of the IoT module, right? So that's these two pins here. And then I've got the reset line coming up to the Arduino here. I then have a pin going across to an LED for flashing it on and off when I receive or send messages. And of course on the other side I've got my DHT22 temperature and humidity module, which is being read by one of the pins on this side. All right, as I said, I'm not going to go into great detail about all of that. You will see the code, but I'm not going to get into depth with it. All right, so next thing is to look at the code.